Okay, guys, good morning. So uh, let us start our class. So before starting, anything you want to ask? No? Okay. So let me screen share. Okay. So uh, yeah, just one thing, guys. I have created a small feedback for you. It will hardly take 1 minute or 2 minutes. You can just press this link and then give your feedback. I just wanted to, get to the idea whether we are moving in the right direction or I should, say change something which probably is not, say serving our purpose. Either it is in my way of teaching or something else. Okay, so I just wanted to improve so that both of us can get benefited from this course. So just go and give your feedback. You can even write a couple of sentences, and I have kept it open throughout the semester, but try to do this in a week so that I can collect your feedbacks after a week, and then plan our say next move. Okay. So in our last class, sorry for the disturbance. So in our last class, a quick review. So we started with our capacitor and capacitance. So we looked at a two conductor capacitor, and we know that a conductor, a conductor, an isolated conductor is a equipotential body. And then when they are, kept between a potential difference, then the charges will start to accumulate on these two conductors. And because of these two, charges creating, you will get an electric field between these two because of the Coulomb's force of attraction. And then we can find the capacitor of this two conductor capacitor as Q over V with this general expression. Then we came up with two methods where we know Q or when we know V. So we were doing the first one when we know Q, which actually involves the Gauss's law. And then these were the steps. We have to go for a coordinate system. Then we put the charges, and first we find the electric field, and then from the electric field, we find the potential difference, and finally the capacitance. Okay, so we took an example of a simple parallel plate capacitor, whose capacitance we have been using maybe since our physics course or our electric circuit, that is C is equal to epsilon naught, epsilon S over D. And then we looked at the energy stored in the capacitor, which is half CV square. And then we also did a partially filled capacitor. And in the partially filled capacitor, remember, because now the field is different in this region and this region. Therefore, what we do, we divide now the electric field as E naught in this region, E1 in this region, and these are the regions, air and the dielectric medium. And then we make sure that they satisfy the boundary condition. So here our electric field is only in the X direction. So the only boundary condition which comes is, yes, which kind of boundary condition will be applicable here? Yes, Mr. Sultan Al-Dosri, can you tell me?
Yes, Doctor.
Yeah, which kind of boundary condition is applicable here? Because if we
Uh,
have electric field only in the x direction, so we have two boundary conditions, right? So which we will
yeah.
apply here?
The perpendicular. We want the perpendicular one.
Yes, the perpendicular one. So can you help in telling what is that perpendicular uh, boundary condition? Do you remember?
I'm not sure actually.
Uh, Please, try to have a quick review of our previous class. Taha, can you tell me? Taha,
Yes.
yeah, can you tell me what is the boundary condition that we have to apply here? Just now your friend has given us the idea. It's the perpendicular boundary condition, or I should say it's the normal boundary, not perpendicular. So what
Where is the D1 minus D2 equals to rho S?
Okay, so D1, we should not say D1, we have to say D1N, because if we are not working with vectors, then we have
the normal.
The D1N minus D2N is equal to rho S. Okay, and since, yes, you're right, it's correct. So we have to use the normal component of the electric flux density. So D1N minus D2N is rho S. So here, this is our boundary. If you see, this is our boundary, because here is the A, here is the dielectric. This is our boundary. And on this boundary, we do not have any charges. That's why rho S becomes 0. And we will end up with D1N is equal to D2N. That is the normal component of the flux density in this region, and this region is same, which is this one. D0 bar is equal to D1 bar. So now I'm directly writing in vector form. Why I am writing in vector form? Because my electric field is made up of only the normal component. That's why. So it is D0 bar must be equal to D1 bar, or epsilon 0 E0 bar must be equal to epsilon 1 E1. So this boundary condition must be satisfied. And now after that, what we did? We found the electric field in this region, which is its magnitude, which is Qs over epsilon 0, right? Qs over epsilon 0, because epsilon 0 is the permittivity here. And here it is Qs over epsilon 1, because we are in this region. And these are the electric field values, magnitudes, and therefore your electric field vector will be in your 0 to D1 region, which is in the dielectric region, it will be this one, and in the air region, it will be this one. And you can check, this will satisfy this condition. So put this epsilon 0 E0 is equal to epsilon 1 E1, they will be equal. So good, the boundary condition is satisfied. That means my electric fields that I derived in these two regions are correct. Then you find the potential difference is minus integral 2 to 1 E bar dot dl, 2 to 1, that is from the lower potential to higher potential. Now, directly going from lower potential 2 to higher potential 1, I'm going in two steps. From here to here, because in this region we have different electric field, and in this region we have different electric field. So that's why it is two step. So first step is E1. So when you put it, you will get E1 D1, which is in the dielectric region, and E0 D0, which is in the air region. And if you substitute E1 D1, you will get this as the potential. And the capacitance will be this one, which is 1 over D1 over S epsilon 1 plus D0 over S epsilon 0. And what is this? You will see that if you rearrange this, you will get this one, which is 1 over C is equal to D1 over S epsilon 1 plus D0 over S epsilon 0. And D1 over S epsilon 1, I can say that It is the capacitance of only this region. Because remember, this expression S epsilon over D is the capacitance expression that we got here. See? So it is the capacitance of this region and the capacitance of this region, and they are as if they are getting added in series. Remember electric circuits? So 1 over C0 plus 1 over C1 is equal to 1 over C. This is as if the capacitors are added in series. Got it? Now you have one more example. Yes, Abdullah.
Doctor, for the tangential component of the electric field, we exclude it because the electric field is in X direction only?
Yes, so the tangential component doesn't exist. So that's why you do not require to make sure that the tangential boundary condition satisfies. You're right. Okay, so now we have another example. So where partially filled capacitor is now in this way, that is, you have some material in here and you have some material here, and this length is L1 and this length is L2. This is D. Now you need to find the electric field. And this is your assignment question. So go ahead and do the assignment question. Okay. And here, what you will see here, you will also have the EX component because you will have only one component of electric field, which is EX component. But in this case, that EX component is becoming tangential. See, because my boundary is this one. My boundary is this one. This is one material. This is another material. So therefore, in this particular case, because this is the boundary, my electric field EX is becoming tangential. So keeping that in the mind, you can solve this example. So you can solve this assignment question. Okay, so I'm leaving it to you. Now, let us take this example. This is a very, very common example. So we did for a parallel plate. Now we want to do it for a spherical, for a cylindrical capacitor. So a cylindrical capacitor. If you see, it's a cylindrical capacitor, or very commonly it is nothing but it's a coaxial cable. It's a coaxial cable. See here, this inner is the inner conductor of the coaxial cable, and this is the outer conductor of the coaxial cable, and between these two conductors you have a dielectric medium, which can be a plastic or which can be Teflon, not Teflon, it can be, I don't remember the name. It's a variation, it's a modified plastic. So that is the dielectric medium. Now, what capacitance will this type of coaxial capacitor give? We are trying to find. And this becomes very crucial, guys, because when you want to use a capacitor, when you want to use a coaxial cable, then the coaxial cable is usually used to transmit, our signals at different frequencies. But till what frequencies you can transmit a signal on a coaxial cable? This is determined by the specifications of the coaxial cable. By the specifications of the coaxial cable, because of this capacitance which we are finding, that is the capacitance which is created between these two conductors, and the resistance, it forms a sort of filter. It forms a sort of filter because it's an RC. So it forms a sort of filter, and therefore that capacitance and the resistance value will decide what is the maximum frequency your coaxial cable can take. That means your coaxial cable can pass that signal through. So it becomes very important, and our And as an engineers, for the coaxial cable, we always want the coaxial cable capacitance to be as small as possible, and the resistance also as small as possible, so that this time constant becomes as small as possible. And this will allow you to take your signal for very long distances. The resistance is small, so therefore the attenuation of your signal will become less, and the capacitance, which creates a filtering effect, the smaller the value of the capacitor, then the longer you can take the higher the frequencies that you can take through your coaxial cable. So this is what we are trying to determine here. And now you can see, why electromagnetics is so important, because with the help of electromagnetics, you can find this capacitance and this resistance. Okay, so what is our problem statement? This is our conductor, and the conductor has a radius of A. This is my outer conductor. This has a radius of B, and this epsilon is the material between them. And this is the length of my conductor L. And I have placed the conductor along the Z-axis. This is the Z-axis. And this is the top view. Top view. So if you see here, this is my central conductor, which is kept at a charge of positive Q. And this is the outer conductor, which is kept at a charge of minus Q. And remember, when I'm putting this minus, I'm referring to this minus on the conductor, because in this region, you will not have any charge, because this is a dielectric region. Your charge is on the inner conductor and the outer conductor. So now how are you going to solve this? Choose a coordinate system. So which coordinate system would be the best for this one?
Cylindrical.
Right? The cylindrical coordinate system, because it's a coaxial cable. Its shape is very similar to a cylinder. So the easiest one is the cylindrical coordinate. So it was cylindrical coordinate. Then assume the charges, which we have already assumed. So, and now we are going to the third one, which is we need to find E. Now, how do we can find E from Q? Because we know Q. How can we find E from Q? Because first we need to find E, and then we will find the potential difference from the electric field. So how are we going to find here? We use Gauss law, because as we have already seen, the first method is based on the Gauss law. So we will find the electric field, because the Gauss law is the law which relates the electric field and the charge. So that's why. So since we know the charge here, we will find the electric field. So what it says, okay, so this is my, okay, so let me make it like this. Okay, so let me now draw here. So now what we are doing here, so this is my inner conductor. This is my outer conductor. So inner conductor has positive charges. Outer conductor has negative charges. Okay. So now what I am doing, now I need to find the electric field in this region, right? The region which is between the two conductors. So I want to use Gauss's law. So in the Gauss's law, what I will do, I have to enclose, in a hypothetical Gauss's surface. So since I need to find the electric field here, so I will enclose this center conductor inside a hypothetical closed surface, which is your cylinder. So if you see here, So this is your length L, right? And this is your center conductor. And my hypothetical cylinder is this one. So my hypothetical cylinder has a radius of rho, and my rho is in between A and B, right? Because I want to find the electric field in this region. Rho is A and B. Now let's go here. Closed surface integral d bar dot ds bar is equal to the charge enclosed. Now let us see how the electric field will be here. So how will be the electric field here? So what will be the direction of the electric field? Yes.
Outside the cylinder.
Yes. So we have two cylinders. If you see here, we have two cylinders. So sorry, the two conductors, this one and this one. So this is negative charge. This is positive charged. So now think about it. Think about your Coulomb's law. Now in the Coulomb's law and also in the Gauss's law that you have studied, how would be the direction of the electric field? Yes, Ramzi, can you tell me?
What, sir?
The direction of the electric field. How would be the electric field here? If this is my positive charge and this is my negative charge. See, this is the positive charge cylinder. This is the negative charge. So how would the electric field from the Coulomb's law?
Go out from positive to the negative.
Negative, yeah. So go out from positive and reach the negative like this. And go out from positive and reach the negative like this. Go out from positive and reach the negative like this. Positive and reach the negative like this. So did you get, guys? Did you get my point? So this is how the electric field will be between the two conductors. That is the electric field in the dielectric region. So it will be in this direction, right? It will be in this direction. And what is this direction? If this is my y-axis, sorry, not y. If this is my z-axis in the cylindrical coordinates, if this is z, escape. If this is z, then what is this direction? Yes, anybody tell me?
Rho.
Rho direction. This is the rho direction, right? So that's why our electric flux density, or since my electric field has only rho component, see, it's only rho component. There is no other component. It's not moving anywhere. It's only in the rho direction. So since it has only rho component, so therefore my electric flux density also will have only rho component. So therefore my electric flux density is d rho a rho. Okay, d rho a rho. Now in this case, our closed surface integral d bar dot ds bar is the charge enclosed. So my d bar is d rho a rho. Now what will be my ds? What will be my ds bar for this one? What will be the ds bar of this one? If this is my small elemental surface, ds of my hypothetical Gauss surface, then its unit vector, its normal will also be in the rho direction. See, it will also be in the rho direction. So my ds bar will be equal to ds, sorry, not ds. It will be d rho a rho. And my d bar is d rho a rho. So if you do the dot product of this, it will be simply d rho times integral of d rho. Okay. And now it will be d rho. So what is the integral of this rho? That means integral of this rho means what? The integral, that is the surface area of this cylinder. Yes, what is the surface area of the cylinder? This cylinder? Yes, of an open cylinder. Do you remember? The surface area. Sorry. Because now, oh. Because now this is our cylinder. See, our Gauss cylinder is this one. Its length is L and its radius is rho. So what is this surface area of your cylinder? Yes?
2 pi rho.
Pi rho L. It is 2 pi rho L. Okay, so that's why this ds, integral of ds, is nothing but the surface area, and which is 2 pi rho L. And by the way, why I am not considering this closed surface and the bottom closed surface? Why I am not considering this? Because it's a closed cylinder. So therefore, this is one surface. This is the top surface. This is the bottom surface. But whatever we are doing here is only for this surface. Surface number 2. I am not doing it for 1 and 3. I am only doing it for 2. I am not doing it for 1 and 3. Yes. Yes, Mr. Hussein Al-Zaki, can you tell me why I am not considering this surface and this surface?
Yes, doctor. I think because the electric field is in the direction of rho.
Yeah, okay, if the electric field is in the direction of rho, so if I dot product that electric flux density with this ds surface, what will happen?
That term will be zero.
Yeah, the dot product will
zero.
become 0. That's why. So guys, again, this is just a review. We are doing a review of Gauss's law, because here my ds will be equal to, sorry, it will not be d rho a rho. It will be, I have to check. I also don't remember. Just give me a minute. Where is the formula sheet? Okay, so let us see the formula sheet from here. Okay, so it is rho d phi, sorry, yes. So it is rho d phi dz a rho. So this is the correct one. Okay, so let me correct it. So it is rho d phi dz a rho. So here it will be rho d phi dz a rho. And since our d has only a rho component, so when I dot product with this, it will exist. But for this case, if this is my ds, then my normal component will be pointing upwards, right? So this will be a z. And for my this one, if this is my ds, then its normal component will be pointing downwards, which is minus az. So if you dot product this d, if you dot product a rho with az, it will become 0. A rho with minus az, it will become 0. So that's why I'm not considering it. I hope it is clear, right? Because we discussed about all we talked about all these things when we were doing the Gauss's law. So this is just a review of the Gauss's law. So that's why I'm considering only this surface, only this surface. And the area of this surface is 2 pi rho L. And therefore my d rho is Q over 2 pi rho L. And hence my d bar is equal to, your d bar is equal to Q over 2 pi rho L A rho. And E bar is equal to what? Just put epsilon there. So 2 pi epsilon rho L A. This is the electric field which is between the two conductors. So wherever you need to find the electric field, you just put a hypothetical surface, and in our case, it's a closed cylinder. And then we apply the Gauss's law. And what we found, that the top surface and the bottom surface of my closed cylinder, it doesn't contribute, you will get 0, and only the side surface will contribute, whose area is 2 pi rho L. So this is the electric field. And once we get the electric field, what is the next step? The next step is, once you get the electric field, the next step is your potential difference is minus integral 2 to 1 E bar dot dl. And by the way, guys, here, okay, I will come back to this. E bar dot dl. So E bar is this one, and dl is d rho. Why dl is d rho? Because my electric field, I'm integrating the electric field. See, I'm integrating the electric field with E bar that I got from this point. So this is my lower potential, 0.2, to higher potential, 0.1. So I'm integrating from here to here. So which direction is this line integral? This line integral is in the d rho direction, right? Because I am integrating from here to here. So this is my rho direction. So that's why for the line integral, this will become d rho. Okay, so that's why here we got d rho, and it's a line integral. And now when you solve this, you will get the potential difference as Q over 2 pi epsilon L, ln of B over A, and the capacitance is 2 pi epsilon L over ln of B over A farad. And have you guys done the second experiment? Yes, the lab.
Yes, we have.
Yes, we did that.
Yes, you did the second experiment. So now
Yes.
you appreciate that this is the capacitance value that you used in that experiment number 2. But again, for a coaxial cable, because this capacitance is distributed throughout the length, so therefore we always go for capacitance per unit length. So because this is the capacitance for the length L of my coaxial cable or a coaxial capacitor. So capacitance per unit length will be C dash, which will be C over L, and it is 2 pi epsilon ln of B over A. Okay, this is the capacitance per unit. And now this will allow us to design the capacitors properly, because it depends on A and B. That is, it depends on the radius of my inner conductor and the outer conductor. So if my inner conductor, if I make it as small as possible, then if I make the inner conductor as small as possible, that means if A approaches 0, then your capacitance will decrease. Your capacitance will go to 0, which is good. This is what we need to do. But we know it very well that, you cannot go to almost 0 radius. because your wire will have some thickness, and this thickness is determined by, you know, various other things. That is, how much is the value of the voltage, sorry, the current that it is carrying and other things. But it is giving us an idea that you can reduce A to reduce the capacitance. And then you have to make B over A. On the other hand, if you have B over A close to 1, if this is becoming close to 1, then log of 1, ln of 1 will become 0 and the capacitance will increase. And the capacitance will increase. That means if the distance between them, because B over A ratio, you can think it as, you know, this one, the distance between them. So as the distance approaches each other, as the distance reduces, that means capacitance will increase. Okay. So using this, we can design a coaxial cable. Okay. Clear? Now from capacitance, now how can you find the resistance of a coaxial cable? Resistance. I'm referring to what resistance? I'm not referring to the conductor resistance. I'm referring to the resistance which is offered by this dielectric region. What is the resistance? So because we know the capacitance, but what is the resistance offered by this dielectric medium? Because no dielectric medium is perfect. No dielectric medium will have, you know, perfect conductivity. That is the conductivity going to 0. The conductivity going to 0. This is a perfect dielectric, but it doesn't exist. So it will offer some resistance. So what is that resistance? Can you find that resistance? Yes. So you can have two approaches, and this is what I'm saying, showing here. You can have two approaches here. Either you use this general expression, because, you know, if the charge is known to you, from the charge you can get the electric field, and from the electric field you can get the potential difference. And once you know the potential difference, then you can find the resistance as V over I, which is my V you have already calculated. Yes, you already got the V. I, how can you find the I? Use the Ohm's law in point form, which is I is integral J bar dot ds bar over the surface, which is equal to J is what? Sigma E bar dot ds, because E bar, you know it. So this is one way to find it. Another way is there is a relationship between the capacitance and the resistance of the dielectric region, or the region separating the two conductors. And it is RC is equal to epsilon over sigma. This is the permittivity, and this is the conductivity. And this is the permittivity and the conductivity of the dielectric region. That is the region which is separating the two conductors. You can use this expression and you can find the resistance, because if you know the capacitance, then R will be sigma epsilon over sigma C. You can use this method. So that's why we are not going and finding the resistance using this method. That's why we are concentrating more on finding the capacitance, because once you know the capacitance, you can find the resistance. Okay, and this RC again is also called as the relaxation time, but here it is the relaxation time of this dielectric medium. Okay, please don't confuse this with the lecture 7, because in lecture 7 also we use the relaxation time, but that is for the conductor. Here it's for this dielectric medium. Okay, it is for this dielectric medium. So this is what I am mentioning here. So what is this resistance here? So in a way, this resistance is, you know, giving it's forming a path for the current to flow from here to here. See, this is R. So if I try to put it in a lumped form, in the form of a lumped component, so it is something like this. Oh, this is bad, because as your signal is moving, this resistance, there is a small current passing through this resistance and a small voltage is developed in this resistance. And this voltage, if you go and look at the electric circuits, this voltage is the leakage voltage, or it is called as the leakage voltage or the leakage current or the leakage resistance. That is, this voltage is being taken away from your signal voltage that is flowing, because the signal voltage which is flowing here is taken away, because here from here your signal will be connected. Sorry, this is plus and this is, so this is plus, this is minus, this is your AC source. So your sine wave, it will be connected here. But as it propagates, because of this leakage, the amplitude or the peak to peak value of the sine wave will slowly attenuate as it travels because of this leakage resistance. And that's why we want this leakage resistance to be as small as possible. Okay. Now we have one more example, so which is a spherical capacitor. So it's not a cylindrical capacitor now, it's a spherical capacitor. That is, it's in the form of a sphere. So you have this a ball, okay, a ball, maybe a soccer ball. So soccer ball surface is your outer conductor, and you can think of another, maybe your which ball should I say? Maybe your baseball, if it is round, and the baseball is inside. And the surface of that baseball is your inner conductor. Surface of the baseball is your inner conductor. And the region between these two surfaces is your dielectric medium. And the inner conductor, which is your baseball, is solid. Is solid. It is made up of complete conductor. It's solid. And this is just the conductor on the surface. And between this baseball and with this soccer ball, the space between them is your dielectric medium. That is your spherical capacitor. Okay. So this one, I'm leaving it to you guys. You can have a look at it. You can go through it. The steps are the same. See, you need to first enclose in here to find the electric field, because how the electric field will be here. Yes, at least let us just discuss about the electric field and leave it. So what will be the electric field here? If this inner ball, solid ball, is positively charged, and my outer ball, soccer ball surface, only is the surface. So the surface is the conductor, is negatively charged. And this is the region between the surface. So how would be the electric field here? Yes, Mr. Hassan Al-Musallam, can you tell me? How would be the electric field here?
Yes.
How would be the electric field here? Just think and say, how would it be the electric field here?
I'm not sure.
You're not sure? You know, we have just now seen for the cylinder, right? As your friend explained. the electric field always directs from the positive charges to the negative charges because of the force of attraction that is coming from the Coulomb's law. So here also it's going from the positive charge to the negative charge. See, the negative charges are here. Positive charge to the negative charge. Positive charge to the negative charge. But here, you know, don't think this as a 2D. Think it in a 3D and think it in the form of a ball. So which direction will be this direction in spherical coordinates?
R direction.
Which direction is it in spherical coordinates?
It's
Going everywhere.
R.
It's a R. It's R, or it is called as radial direction.
yes.
So the electric field will be in R, or the radial direction. And you can use that, and then you can, you know, in a very similar way, you can solve for the electric field by putting again a spherical shell here, which is our Gauss's surface, closed surface, and then you will find the electric field, and then you will find the potential, and then you can find the capacitance. Okay, so this one I am leaving it to you. And the next question is, how do you find the energy? So how can you find the energy stored in a spherical capacitor, or in a way energy stored in any type of capacitor? Yes, we know it. What is the energy stored in a capacitor? Is half CV square, or half Q square over C. And as I told you, this expression, we derived it for parallel plate capacitor, but this is valid for any two type of capacitors. It is valid for any two type of capacitors. So for a spherical capacitor, if I know V, then you just substitute, or if you know capacitance, and so if you know V and capacitance, then substitute here, or if you know just a capacitance, substitute here. That's it. So the capacitance of a spherical capacitor from the previous example is this one, which is 4 pi epsilon over 1 over A minus 1 over B. So once I know the capacitance, I can substitute the capacitance here. I can use this expression, this one. So it is Q square over C. C is the capacitance. And this is the answer. And this is the first method. That is the method 1. Method 1. Now, method 2, what we are doing? Method 2 is we are finding it from. So method 1 is half CV square, or half Q square over C. We got it. Method 2 is our typical method. In the typical method, what do we have? If we know the electric field, then you find first the energy density, which is half epsilon E square. From the energy density, you can find the energy, which is integral of the energy density over the volume. You can do that. So the method 1 and method 2. So in method 2, you have the electric field. So from the electric field, find the energy density. This is the energy density. Got it. Now integrate it over the volume. Now the question, what will be the volume here? Yes? Can anybody tell me before we conclude our class, what will be the volume here? Mr. Abdul Rahman Al-Najim, maybe you can help. What will be the volume here?
Yes, doctor.
What will be the volume here? Because to find the energy stored in a capacitor, we want to integrate it over the volume. So what will be the volume here? This is my inner conductor. This is my outer conductor. Yes, Mr. Najim?
So the region between the two conductors.
Exactly, because your electric field is existing here, right? Guys, my electric field is in between these two conductors. It is radial, it is between these two conductors. So because the electric field is existing in these two conductors, the energy will be carried by the electric field. So therefore, you need to integrate it you have to integrate it in this volume, that is the volume which is between the center conductor and the outer conductor. So which will be this one. See? So for phi full complete unit, values from 0 to 2 pi, for theta is equal to the complete value from 0 to pi, but for r it is only from here to here, that is from A to B. And if you solve it, you will get the same answer. Okay, so we will stop here and